I already know pressure pretty well, so I won't really spend too much time on this. Pressure is force over area. So if I want to change pressure, I either have to change the force or the area or both. For example, if I clench my hand into a fist and I push it against my leg, if I want to increase the pressure, I have to increase either the force or I have to decrease the area. But let us hold the area constant for now. If I hold the area constant, in order to increase the pressure, I need to increase the force. So I push down harder. If I want to decrease the pressure, I could not push down as hard. Now, if I held the force constant, in order to increase or decrease the pressure, I have to change the area. In order to increase the pressure, I would have to decrease the area, because I would be dividing the force by a smaller number. So instead of pushing down with equal force with my fist, I'm going to push down with a single finger. And I can feel my leg, the difference in pressure is increased by a lot. Now if I wanted to decrease the pressure, I could change from a fist to an open palm. Push down with the same force and the pressure is much, much less, because the area is increased. So therefore the force is divided by a larger number. So that's the basic idea of pressure. I'm mainly going to be dealing, for now, with gases. And the pressure of gases is measured in a lot of different ways. But in chemistry, I'm mainly going to be using atmospheres, which is abbreviated ATM. Now, an atmosphere is the pressure of the atmosphere at sea level. The pressure that the atmosphere exerts on the things on the surface at sea level. And there are a few other ways of expressing pressure. One is in millimeters of mercury. 1 atmosphere is equal to 760 millimeters of mercury. So this is how far the atmosphere can push or force mercury up a tube at sea level. And this measurement comes from the original experiments with atmospheric pressure. Sometimes millimeters mercury is called torr. And millimeters mercury is basically changed to torr in honor of the man who discovered this. He was a student of Galileo's, Torricelli. So it's named in his honor, but it's the same thing, millimeters mercury, torr. There's also one more unit which I've only ever come across one time in a very old book, and that is the Pascal. And I never really have seen this anywhere except for a very old book. I think it was an original. It was not an original, but it was a reprint of the original, and it was a 200-year-old book by a French scientist. And I believe they used to use Pascals quite commonly back then. I'm not sure exactly when the switch was made, but Pascals are, I've never really seen them, so I wouldn't really worry about them too much. The more common ones I'll see are atmospheres and millimeters of mercury. And also I've seen pounds per square inch. Whenever I've gone diving, all of my tanks are in PSI. But in chemistry, PSI is not used that much. I'm mainly going to be dealing with millimeters of mercury and atmospheres. And that's all there really is to know about pressure. Just the fact that it's force over area, gases exert pressure. And the relationship between pressure and volume and the amounts of gas and the temperature are all things that I'm going to go over in successive parts of this book. Charles' law, Boyle's law. I can't remember what the other guy was, but they're all going to be related to pressure. And I guess I may as well mention this experiment very briefly since I brought it up. What Torricelli did was he took a tube of mercury inverted it in a dish of mercury. And obviously what he was expecting was all of this mercury just to fall back into the dish, but that did not happen. What ended up happening was that the mercury stayed at around a level of 760 millimeters at sea level. And this was not at all expected. Normally when things are dropped, especially since this is a liquid and not a solid, normally when things are dropped, they fall to the ground. But this very, very dense liquid seems to be defying gravity. Mercury is many, many more times dense than water. So it was very, very surprising that this would be seeming to defy gravity. So eventually they came to the conclusion that the atmospheric gases were exerting force on mercury. It was pushing the mercury down. Gases are very much like liquids, where they try to fill any container. So as this gas is trying to fill the entire Earth evenly, it can't, there's a vacuum right here. So when the atmosphere is applying pressure everywhere, it's pushing downwards on mercury. Now normally mercury in a dish that doesn't have a vacuum would just stay there because mercury would push, or the atmosphere would push on mercury and the mercury would push back. But here, since there's a vacuum, it's pushing, and then all this force is pushing it back up, and then the mercury back here can't push back because there's a vacuum. So I guess that's sort of like a lesson in physics. I guess that would make sense to a physicist. But that's really what's going on. If there had been a gas in here, if this had been filled with gas, then this wouldn't happen. Well, then the gas would push on the mercury, and then it would get to a point where the pressure in the inside would equal to the atmospheric pressure. But I guess I wouldn't know that just yet. I guess let me put it in the example of a rubber ducky or a balloon. So when I put air into a balloon, I'm adding more gas in here and I'm increasing the pressure. And the balloon expands. I'll put it in here. The balloon is going to expand until the pressure on the inside is equal to the pressure on the outside, atmospheric pressure. If the pressure on the inside is greater, then it would continue expanding because this would have more force. It's basically like two people pushing against each other. The person who's pushing harder is going to push the other one back. That's why it expands. So that's the basic idea of these different pressure, and that's how a lot of these gas laws are going to be looking into what's going to happen when more gas is added, what's going to happen to the volume, what's going to happen to the temperature, what's going to happen to the pressure.